We're going to spend the last section of the workshop talking about some advanced tools that make their way into the reconnaissance, not at the onset of the reconnaissance, but typically the second phase. So we're going to talk about terrestrial LIDAR data collection that we can carry into the field. That's tripod LIDAR. The use of some lightweight instrumentation that allows us to get geotechnical profiles into the subsurface. The two being the spectral analysis of surface waves or multi-channel assessment of surface waves, and dynamic CPT, which is you definitely want to have a grad student who's a football player join you to drop that weight. And then Scott is going to come and talk about UAVs and the ability to collect photographs and other information using unmanned robotic quadcopter and hexacopter systems. Okay, so typically what happens in a reconnaissance is that the phase one group goes out. They do what you just did outside, which is just make the observations, cover the landscape, get the spatial extent of damage, where it's extreme, where it's minor. We as geotechnical engineers and earth scientists tend to have a very spatial sense about this. If you participate in an EERI reconnaissance that has structural engineers, you find out that their sense of spatial landscape are building types. They don't really care where the building is, that they're more interested in getting into the building and looking at the floor to column ratios and the way that the rebars joined and all the fine details in the structure. So we have a very different sense in the way we go about our data collection than, say, an EERI structural reconnaissance typically does. One of the tools that we found that's very useful for capturing three-dimensional high-resolution imagery are a various suite of systems that are based on scanning lasers, so LIDAR systems or rangefinders. And in my lab, I have 3 of these units. I have the 3 of them are all Riggle units. And it's one flavor of LIDAR. So LIDAR comes in either phase-based systems or time-based systems. The units that I have are all time-based. So in a sense, there's some advantages to having a phase-based system in terms of wave analysis that we can't do. So we're just interested in the time of flight on a two-way travel time from the scanner out to a target and returning. And so the speed of light, which is c, times the number of nanoseconds that it flies from here out to the target, divided by 2, is the one-way travel time related distance. So that's how we calculate distance with the scanners. These units are using a YAG neodymium laser. It's a near-infrared, 1064 nanometers. It's eye safe. It's low power and it's eye safe. So we can scan in the room right here. We could scan all of you with your eyes open, and there would be no damage. So it's really a very useful tool to have on a reconnaissance. Often, in some of the landscape that we work in for reconnaissance, it's a dangerous place, just like Oso was it's a moving landslide. And so in the old school, we would actually be putting boots on the ground to make measurements and exposing people to risk. One of the nice things about LIDAR is you can stand outside of the zone of movement and you can capture this data without exposing anyone on the reconnaissance team to imminent danger. When we do an analysis and it's in a controlled environment, not an earthquake reconnaissance, you have all the time and luxury to do things right. You can set up reflectors. You can have a DGPS system to very tightly control and geolocate where your scanner is, where your targets are in the field. And so this is a typical kind of thing where we would have a photogrammetric camera that creates its own point cloud. We have the scanner. We have a DGPS unit. It's great. Takes a lot of time. It's slow, but it collects great data. When we operate in an earthquake reconnaissance, it's the exact opposite. It's fast. John has just given us a list of a dozen sites spread out 200 miles. We have very little time to capture that data before it's modified, and so we are moving really fast to do this data collection. We don't put up a lot of reflectors in the field. We don't bring differential GPS. We do a relative registration and then a coarse geo-registration or geo-referencing of that data set. The whiteboards that you used out in the exercise turn out to be great for LIDAR. Like in LIDAR, it's just like going to 50 sites on a reconnaissance. You can't remember how you did your setup 10 scan sites ago because you've collected something like 100 scans or 200 scans that you need to register into individual data sets. So we use a lot of these low-tech tools. This is blurry, unfortunately. Low-tech tools like this to do exactly that, to basically to remember every site and how we set up on that site so we can best pull the LIDAR data together. So it tend to be very much sort of low budget and very fast operations collecting LIDAR for a reconnaissance. So the 4 steps that we go through when we collect LIDAR data sets is that we first go out to the field, of course, when we do our scanning of sites. We scan from multiple orientations to remove shadow zones. So if I scan you from the front of the room, I can see the front of your faces. It's lovely, but I know nothing about the back of you. And I also know nothing about the areas behind you that the LIDAR scanner can't see because you're casting a shadow over much of the field. So we move the scanner around to different orientations to try to fill in these shadow zones. If we've done a good job, then we're going to have a triangular or regular network or a tin surface that we fuse that's going to have small network triangles. And if we have big gaps and openings, we end up having to fill them with very large facets that don't really represent the landscape. Once we have the tin, then we can do all the metrics that we need to do, for example, change detection on a site, pre and post earthquake deformations, for example, or the volumes of a landslide movement or material at the toe of a landslide, or distances. So these are very simplified, the 4 procedural steps that you would go through to do a LIDAR analysis. So John talked this morning about the Condominios Presidentes, 4 buildings named after presidents of Chile, 2 of which were badly damaged. There are these 2 in the front, and 2 back here that did not have settlement. We visited the site in the second phase of the reconnaissance. They had gone to some 50+ sites, of which we targeted something like 8 in the Chilean earthquake to capture for LIDAR and for dynamic cone penetration testing. So Scott Olson is in the picture in the top left, and he's doing this dynamic cone penetration testing, which is about the crudest thing you could do on the planet. And we're over in the other corner scanning the whole site with the laser. So it was like, you know, Buzz Lightyear meets the Flintstones. The way we analyze the deformations in the 4 president buildings is that we hung an artificial primitive surface that was perfectly horizontal digitally over these buildings. They were all built to the same design. They were identical buildings. And we measured from this hypothetical surface the distance to the various corners of the buildings. So 16 measurements on 4 buildings. And what we found was the 2 buildings in the foreground don't have much in the way of differential settlements at all. So this Boldness building has basically 0 deformation. This building has uniform height difference of something like 2 centimeters. it may not have settled at all. It just might be a building that's 2 centimeters shorter than the building on the right. The two buildings in the foreground, things are happening. So, for example, let's just assume that no settlement occurred in the top right building, so that 6.9 centimeter you could set to 0. Then you have at least some tilting of that building going on, or something like 28 centimeters. But we have the benefit of John's measurements in the field to show that there's settlement that occurred in that corner of the building that's estimated to be something like 7 centimeters. So in fact, these probably represent the true settlement of that structure relative to its adjacent structure. So this is a way that we would use LIDAR data capture in the field to measure differential settlements in structures. So none of you have been to these condominiums in Chile, but a second aspect of this is the educational aspect, that you can take a visit to these structures years after the earthquake and experience the damage. So here, for example, we're flying around these condominiums and you see the foundation settlement occurring right here along the pad of the Riesco building, which is the one that had the maximum amount of settlements, off here on the right. The maximum amount of damage was happening right in that inner corner of the structure. And you'll get a sense of what the landscape looked like for this damage. So we have the actual metrics that we're making the measurements on to calculate the quantity of deformation. And then we have visuals like this that familiarize you with the site. Okay, another example that's sort of educational tool. There was a dam break in the Tohoku earthquake of the 2011 magnitude 9 event. We didn't have LIDAR data for the pre-failure, but we do have the engineering drawings. So based on the engineering drawings, we could make an artificial dam and difference that against the LIDAR data that we captured of the dam break. From these two, the architectural drawings that allowed us to make a primitive dam and the actual field deformations, we could calculate how much breach occurred, where the breach occurred through the foundation of the dam.